Good morning, students. Today's lecture of TOC, we are going to understand about what is, regular context-free language. Now, before making you understand about context-free languages, definitely what we have done in the prior, we'll see what type of relations is there in between context-free language and regular language. See, what we have done prior was regular grammar give rise to regular language, and regular language gives rise to finite automata, which could be deterministic, or non-deterministic, right? Non-deterministic. Similarly, we have when we are talking about context-free language, then context-free grammar give rise to context-free language, and context-free language give rise to push-down automata. Push-down automata, right? So can you see what is the difference? See what is the similarity. Here we have regular grammar, then we have context-free grammar. Regular grammar give rise to regular language, and regular language further give rise to finite automata, which could be deterministic or non-deterministic. Similarly, context-free grammar, from context-free grammar we can get context-free language, and context-free language we can be taken by push-down automata, which can again be non-deterministic or deterministic. Now you see the similarity. This automation is more stronger than regular grammar or regular context-free grammar. So this is more powerful as compared to this one. Now, if we have to describe context-free grammar, context-free language, so how you are going to define what is context-free language? See, we can define in general. If you have to define what is context-free language, then the language which is being provided by context-free grammar can be termed as context-free language. Any context-free grammars give rise to language. The language which is being provided by context-free grammar can be termed as context-free language. And roughly, secondly, if you have to understand, see, we don't have any direct definition to make you understand what is context-free language. So again, any context-free language which can give rise, of which we can create push-down automata can be termed as context-free language. So these are the two ways by which we are going to define what is context-free language, right? Now, so this is clear to you all, right? So what exactly is happening over here is, see, context-free grammar is giving rise to context-free language, and from context-free language can generate push-down automata, and push-down automata can be of two types, that is deterministic push-down automata or non-deterministic push-down automata. This is deterministic push-down automata, right? Automata, and this one is non-deterministic push-down automata. Right? This is clear. Now, for all the, if you have to compare between deterministic push-down automata and non-deterministic automata, how we are going to define it? See, for all the context-free language we can generate non-deterministic push-down automata, but for all context-free language we cannot generate deterministic, not for all. We cannot, not for all. You can write it here, not for all. So what is the basic difference? We can create non-deterministic push-down automata for all the context-free language, whereas deterministic push-down automata cannot be created for all context-free language. There are few context-free language for which we can generate deterministic push-down automata, right? This is clear. Now we'll understand what is push-down automata. See, we have push-down automata. Push-down automata. See, push down automata is actually having 7 tuples. How many tuples they are having? 7 tuples. You can define 7 tuples. What are those 7 tuples? It can be defined as PDA has 7 tuples: Q, sigma, Q naught, F, then we have Z naught and tau, and transition for we have delta. See, these 4 tuples are somewhat similar, that is Q, states, number of states. Then we have sigma, which denotes the inputs, just like we have in finite automata. In push down automata also we have these 4 tuples same. 5 tuples are same. Only 2 new tuples is being introduced, that is Z naught and tau. So Q, what does the Q denotes? Number of states, then sigma input, then Q naught denotes the initial state, and F denotes the final state, whereas delta denotes the transition. So these are all same as now the 2 new tuples, that is Z naught and tau, that is what we are going to discuss. Now before discussing it further, I would like to mention you about the architecture of push down automata. See, what we have in push down automata, say this is cells, right? Say the string inside is xz, right? And this is null string. This is what? Input tape, right? Then what we had? Reader header. Then we have finite control unit, right? And this is, say, Z naught. This is stack, push, pop, right? So these are the various things. Now, as you can see in this architecture, see, input tapes contains each cell is having their independent string inside it. Then we have reader header, which actually heads towards the one cell at a time. Then we have finite control unit. So this structure is somewhat similar to deterministic automata only. Are you getting? This is somewhat similar to automata only. The only difference that has come in the push down automata is the presence of stack. This stack is added. So if we have to define what is push down automata, then we can define it that push down automata is a combination of finite automata plus stack, right? You can see here, this is the architecture of finite automata and this is the stack. So when we combine the finite automata with the stack, then it comes out to be a push down automata architecture. This is clear. This is somewhat similar as finite automata, and this is something stack. Stack is, what are the 2 operations that is performed in the stack is push and pop operation, right? So the 2 things, that is one thing that is additional is stacks, and if we include the stack in it, then the push down automata is being created. Now see, one thing that we need to understand is that we have 2 operations. See, why we need this in data structure. What is the use of data structure? See, data structure is used to manage the memory, right? In this we have push operation, in which we insert the data. When we insert the data, we check. What we check? Is there any space to put? That data inside? There should be some space. If space will not be there, then it will overflow. So we need to check whether the space is available to insert the data or not, to avoid the overflow conditions. Then we have pop. What does the pop? What is the condition? Underflow. Pop means removing, right? So what is the use of data structure? So data structure is used to manage memory. Then we have, in case of stack, we have push and pop stack, right? Before pushing any data or string inside it, we check whether the availability to keep that data is there or not. That is overflow. And before, when you want to pop certain strings, we check underflow condition. Now what is underflow condition? In underflow condition, we check whether the string that we are willing to remove or we are willing to delete exists or not. So these 2 terms are clear to you, what is overflow and what is underflow conditions, right? So This is clear what is underflow and what is overflow condition. So now we are going to discuss about the tuples. This is clear. What is push down automata? Push down automata is the finite automata plus stack and stack which check the overflow and underflow conditions. Now we were discussing about push down automata tuples. So we have, how many tuples do we have? We have 7 tuples, that is Q, sigma, Q naught, F, Z naught, tau and delta. Now Q, what does the Q denote? Q denotes finite sets of state. Finite set of state. Then we have sigma. What does sigma implies? Sigma implies input alphabet. Input alphabet. Right? Then comes the Q naught. What does Q naught denotes? Initial state. Then comes the F. What does F? Is the final state, set of final state. What is F? F is set of final state. Then we have delta. What does delta denote? Transition. So these 5 are somewhat similar to finite automata that we have discussed. Now the additional 2 tuples that are introduced is tau and Z naught. So tau is the stack alphabet, denotes stack alphabet, and Z naught bottom or initial stack symbol. Now what is the role of this Z naught? See, in this architecture I have drawn Z naught at the end of the stack. We place it at the bottom. So what is the use of this Z naught? See, Z naught denotes whether the stack is empty or not. What we have done, in order to check whether the data which is or string which is introduced into the stack is there or it is finished, there should be something which indicates okay, fine, this now all the strings inside the stack is finished. So this is that symbols which actually indicates or tell us that the stack is empty now, right? So what is the role of Z naught? Z naught is just like, for example, there is one child. We have a queue, and in the end of the queue we let a child sit, and the child mentioned when all the alphabets gets finished, then the child stand up and stay. Okay, fine, the stack is empty, we don't have any alphabet with us. So you can compare Z naught with that child, that what it is doing, it is mentioning us now the stack is empty, there is nothing to be pushed or pop inside it, to be taken out from it. Okay, so this is clear. Now the tuples are clear. What is push down automata is clear. The architecture of push down automata is clear, and CFL is clear. Now in the next lecture we are going to take certain numericals. Thanks for watching this video for today.